Hello, everybody. This is going to be a presentation on hearing, and of course, you're going to get everything that you would normally get from going to class without having to look at me. And so that's an extreme bonus, I would assume, for you. It's kind of the point of this lecture, anyway. You don't have to see me. We're going to be talking about hearing, and so without further ado, let's get moving. We'll start with a kind of a morbid question. Would you rather be deaf or blind? I mean, hopefully you'll never have to make that choice. But consider this. Most people would choose the absolute favorite sense, possibly. You wrote this. I know many of you did when we did the minute paper last week. You chose sight as your favorite sense. But think about it. There are many advantages of hearing over vision. Okay, for instance, things we take for granted like music. Most of you, if not all, certainly appreciate music and listen to it on a daily basis, all right, and get a lot of enjoyment out of it. How about speech? This is a big part of being a human being. Speech. You can hear, communicate, pick up on subtleties of emotion, express new ideas, all of these things with speech. How about this, too? You can't see around corners or through a wall, for that matter, but you can hear around corners. And that's quite an advantage in terms of survival. Okay, how about Helen Keller? You guys have probably heard of her. 18 months old. She was born with the ability to hear and see, but about 18 months old, contracted, I believe, scarlet fever, and it did a number on her. Of course, it rendered her blind and deaf. It's virtually impossible to imagine what that would be like. Check out what she says. She can actually speak to this. She says, I would rather be blind than deaf. Blindness isolates you from things, but deafness isolates you from people. Okay, so think about that, and you may argue that, well, she didn't experience much of life and get the vivid visual experience that maybe many of us have, as you advance through life. But nevertheless, an interesting thing to think about. Light gives us vision. What's the stimulus for hearing? Fairly obvious. It's sound. Okay, but what is sound? We'll get into that in a second. The question, the philosophical, great question that you've probably heard before. If a tree fell in the forest, no one's there to hear it, would there be a sound? Well, it depends, actually. To answer this question intelligently, you need to define what sound is. But the more pressing question, I think, is from Velociraptor. If a man speaks in the forest and there is no woman around to hear him, is he still wrong? You thought you were going to escape the silly jokes. Well, think again. Okay, back on. Sound can be defined in a couple of ways. So when somebody asks you that question, if a tree fell in the forest, etc., you say, well, it depends. Depends on how you define sound. Okay, you have the physical definition. Sound is changes in pressure in air or other medium. Another medium, like water, for instance. This is called compression and rarefaction, technically. And you also have the perceptual definition. Sound is the experience we have when we hear. So, if you define sound physically and the tree fell, and, well, of course there's sound. There are air pressure waves in air that occur when the tree falls. But if you define it perceptually, well, then, of course, no, there's no one around to hear it, so there is no sound. Both answers are right. You qualify it with how you define sound. Sound requires a medium to travel in. Okay? For instance, air, water, metal, something solid. Anything solid, actually, would do too. There is, unfortunately, I think, for outer space, Star Wars fans, there's no sound in outer space, in a vacuum. All right, sound needs a medium. Light does not. Light can travel, obviously, through a vacuum. It's how we get light to the Earth from the sun. So, the laser sounds and things that you get in a space, flick, they're contrived, all right? I'm glad they have the sound effects, but technically it can't actually happen. So, these waves require something to travel through. Sound travels 761 miles an hour. Okay, it's pretty fast. It's a turtle compared to light, but nevertheless, fairly fast. 4 times as fast, however, in water. It goes faster through something that's more more solid. Okay, for instance, water. If you've ever been underwater and tapped a couple of rocks together, you'll note that you can have a friend underwater 100 feet away, Olympic pool or something like that, tap little pebbles together. And you can hear even the lightest tap. It's very efficient, these waves traveling through water. And it will sound, like it happens instantaneously, because it's much faster than it occurs in air. Well, check this out. 15 times as fast sound traveling through metal. That's pretty incredible. So it actually travels faster the more solid the medium. All right. A couple of cool things that I got to witness personally when I was working for the Air Force. And then also something maybe you're interested in. It's not anything I'm going to technically probably test you on, but nevertheless interesting, a sonic boom. When an aircraft, generally speaking, not a commercial airliner, they usually are under 600 miles an hour, but if you have an aircraft like a military jet approach and bust through 761 miles an hour, you get this loud, extremely loud, low-frequency boom. What causes that? Well, I'll tell you. Again, super low frequencies, which means that it's kind of like the bass in a song, like a hip-hop song or whatever. Extremely low. Well, here's an illustration of what happens. And so you go from one, which is referred to as subsonic. You're not quite reaching the sound barrier. And you see these waves, the sound waves that are emanating from the front of the jet. They are still being pushed out in front of the jet. The jet's not flying fast enough to catch up to them. All right? And 2, Mach 1, which is the sound barrier, the 761 miles an hour, the waves are, you're catching up just perfectly to the waves of sound that are coming off the front of the jet. Okay, now when you reach that point, the waves don't have anywhere else to go, and they compress, and they are forced together, and they explode. Basically, they boom, emanate this massive boom. Okay, the sonic boom. As you pass through it, number 3 there, supersonic, beyond the speed of sound. So hopefully that makes sense. The picture of it is really Clyde. This is an F-18 Hornet breaking through the sound barrier, and you see the water droplets, because of the boom, condense together. This wave of shock wave causes it to look like it's coming out of a cloud, just emanating out of nothing. But anyway, so that's what a sonic boom can cause. You might ask, well, does the pilot hear this thing? I've talked to Air Force pilots, and they say no, they don't actually hear it. Some of them do report seeing, the cloud, the condensed waves, and they feel it slightly. Okay, so there's a little bit of a sensation of a feeling, but they, for whatever reason, it passes behind the jet too quickly for them to hear it. Now, I said low frequency, high frequency. Well, what does that mean? Some of you probably have that concept in your minds, what that means. Frequency is, or was, basically characterized by Heinrich Hertz, and this is the unit, Hertz. Low frequencies have a low value of Hertz, say 100 Hertz. High frequencies have a higher value, like 20,000 Hertz. Now, what that means is that if you look at this wave, this pressure wave traveling through, let's say, air, a wave such as this pictured here with the orange line propagating through air, this, let's say, is 100 Hertz. That means that on this scale, from peak to peak, we're talking about it goes 100 times in 1 second from peak to peak. So it would be going up and down 100 times in a second's time. So the sound wave cycles per second. Of course, a higher frequency would repeat, say, 1,000 times in a second. All right, and so we perceive low frequency sounds as having a low pitch and high frequencies as having a high pitch, sort of like on a piano. To the left, of course, we have the lower pitch, low frequency sounds. Up on the right part of the scale, we have the high frequencies. And that's Heinrich Hertz. All right. Interesting facts excuse me, about frequency. Low frequencies travel more slowly. Okay, more slowly, much more slowly actually, than high frequency sounds. However, low frequency sounds travel much farther than high frequency sounds. And you hear thunder, for instance. This is a great example. Thunder you can hear from a long way off. Okay, the low aspect, a low frequency aspect of it. If you've ever experienced, of course, thunder is lightning. It's the sound that lightning makes. They aren't really two separate phenomena. But if you've ever experienced thunder from a long way off, you hear the rumble, the brrrr, that kind of stuff, right? If you're right on top of a storm, or I should say the storm's on top of you, then you hear the crack, the high frequency part of the lightning hitting, okay, and then the boom that follows afterwards. And that is illustrative of both the speed of the sound and the fact that low frequency sounds travel farther, right? So you've got the crack of the lightning happening, that higher frequency getting to your ears faster than the rumble that happens afterwards, okay? And also, when the storm is sufficiently far away, the low frequencies are all that make it to your ear. Another example of that is in like a car audio system with, a lot of bass, okay, huge speakers in the trunk or whatever. From a long way away, you can hear the boom, 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 right? And when the car gets closer to you, then you can start to hear maybe the vocal content or, the drums, other aspects of the sound of the song. All right. What are we sensitive to? Again, people say, well, our ears are great. Our vision is the best. Well, not necessarily. We're tuned to what is ideal for us, okay, to survive in our environment. And what that ends up becoming for us is a sensitivity to from about 20 hertz, 20 cycles per second, up to 20,000. We've got a massive range of hearing, and that's pretty cool. You can hear all sorts of sounds. Right? A lot of variability, particularly in the high end. So we start to lose that high frequency, really high frequency perception. Many of you can probably still hear the whine of a television set, that really high pitched, it's almost annoying, especially older television sets. If you're around those, you can hear a whine, and an older person like me, can't actually hear that whine. It's gone, all right? And so that's just something that goes early. And even for some of you, maybe all you can hear up to is about 16 or 17,000 hertz. If I were in class today teaching you this, I would probably try and test your high frequency perception. I once had a student in New Hampshire, and I did this test in class, and she could hear up to 24,000 hertz. It's unbelievable. That's extremely rare to begin with, even in a very young person, but it's even more rare in a college-aged student. Because even at your age, I know you're all young pups or whatever, but you've lost a little bit, okay, just by virtue of, not necessarily listening to loud music or whatever, but just by experiencing sounds in the real world. That can wear down the high frequency aspect of your hearing receptors. We'll talk about that in a little bit here. So 24,000 hertz, and I was careful. I had a button that was hidden, and I would push it up in front of class, and as I increased 16, 17, 18, people would raise their hands. When I'd push the button, I'd pretend to push the button. They'd raise their hands. I say, "You're out. You're cheated. You can't stay in the game." This girl who sat in the back of the class, every time I pushed it, 20, 21, 22,000, she'd raise her hand. And the other students are like, right, there's no way you're hearing that. And I'm like, she's actually hearing this because I'm trying to fake her out, and she's only raising her hand when it's up. And I asked her, I was fascinated, I asked her what her auditory experience is like, and she says, well, things that don't bother people normally really bother me, like the squeal of bus brakes. You hear that walking along campus, and you hear the bus, the squeal of the brakes, and that would almost make her, hit the ground. It was so incredibly loud, because there are higher frequencies that, we normal people can't hear, can't process, and apparently those are really grating and annoying to her, and so she could obviously process those. So pretty interesting. Many animals. I said, humans are humans. We're tuned to what what serves us well, helps us survive. Check out the elephant. Can hear extremely low frequencies, down to 5 cycles per second, 5 hertz. Dogs in general can hear, actually, it's mislabeled here probably, they generally can hear a little bit lower than we can. If you've ever had a pet dog, you know that a lot of them get nervous when thunder approaches. Sometimes they start acting nervous before you can even hear the thunder. And you're like, well, what's going on? Why are you nervous? And the fact is they can hear those low frequencies a little bit more effectively than we can. So typically, even though it's labeled here as the dog ranging from about 50 way up to 45,000, it's probably closer to 18, 15 hertz up to 45,000. Okay, and that's another thing. Look at that, way up to 45. A cat, 65,000. They can hear very faint, high frequency information. So incredibly sensitive. A beluga whale. Hey, you want to know what a beluga whale can hear? Way up to 120,000 hertz. A dolphin, 150. Remember, these high frequencies travel fast. It allows these animals that can hear very high frequencies, like a bat or a dolphin, to precisely locate objects because it gets there fast. Their ears do the calculation, and they can locate objects. Elephants, I mentioned, can hear down to about 5 hertz. A few years ago, there was that terrible tsunami, a Christmas Day, that injured and killed many people. The elephants heard the low-frequency waves. Okay, some people speculate they may have also felt them in the ground. So by combination of both of those, they started stampeding inland, and people were looking at the elephants going, what are you doing? Oh my gosh, the elephant's going inland. They ran inland a few miles, far enough, as it turns out, to be protected from the tsunami that hit land a couple of hours later. Bats, super high frequencies. They use echolocation. They emit these high frequencies. Those frequencies bounce off of insects, and they can localize those insects. And of course, that's enables them. It's very effective in locating insects so they can eat them. All right, they're amazing. It looks like bats are flying just spastically, randomly all through the sky. They're actually adjusting ever so slightly their flight pattern to usually get an insect, all right, out of the sky. It's pretty incredible if you see one of those sort of in slow motion. I think there are videos on that. Okay, dolphins, check this out, way up to 150,000 hertz. What does that sound like, 150,000 hertz? Well, we'll never know. We can't actually hear it, but dolphins can. And there are tests. Dolphins are very smart, and they've been tested pretty extensively in terms of their auditory performance. They can echolocate a little coin. If you tap a couple of coins together, 70 meters away, okay, approaching the length of a football field, underwater, boop, the dolphin can perfectly point to it and swim right to it. It's pretty incredible if you ask me. All right, owls, amazing hunters. For a variety of reasons. They can fly silently from 50 yards away in 10,000ths of a second, can locate a mouse's squeak. And just the fact that you can actually hear a sound from a mouse's squeak from 50 yards away is pretty impressive. They can locate it. Obviously, they hear it, and they're like, food, dinner time, going after it. Again, just in case you wanted to know the auditory range hearing ability of a raccoon or an opossum, a gerbil. Take your pick. I've got different creatures here. It's kind of interesting how much variability there is. And remember, yeah, it's not that, because a chicken can only hear from 100 up to 9,000, that it's a dumb animal. It's just that is what, a chicken's maybe not that smart, but a poor example, I guess. But it serves the chicken well. This is what the chicken needs to get by. Okay, it doesn't need to hear super low frequencies or super high frequencies, right? Okay, neat information there for you if you're interested. Amplitude and frequency correspond to loudness and pitch. So again, if you want to speak physically about a sound wave, you talk about its amplitude and pitch. I'm sorry, amplitude and frequency. So loudness is the psychological correlate to amplitude. So if a wave has high amplitude, we generally would say that's loud. Okay, and then of course correspondingly pitch is the psychological correlate to frequency. We would say if something has a high frequency, physically speaking, we would say, oh, that's a high-pitched sound. Okay, and then illustrated by this figure here. You can see the low frequency at the very top. It's spread apart more, okay, and higher frequencies, the waves are occurring more frequently. They have a higher frequency. The amplitude, looking at the third wave from the top, it has a shallow profile. That's low amplitude. Higher, you see the profile grow taller, okay, and that's a wave with a higher amplitude. We'd say that's louder, okay. Decibels. Speaking of loudness, people talk about this. It's at least 100 decibels you might hear, or something like that. Well, what is a decibel? Well, it's a scale, the decibel scale. Generally speaking, and of course, the higher the decibels, the louder something is, the higher the pressure, these waves. And I've got some information up here on iPods, other music devices and stuff like that. You've got these earbuds that are right there, dangerously close, as it turns out, to your hearing apparatus. You can do damage, and I've got some information here, a link to an article that talks about it a little bit. But be smart about it. I like music as much as anybody, trust me, and sometimes loud music is better. It just is. I understand, but you got to be smart about it. Again, I played in bands and stuff when I was back in Phoenix in college, and you can pretty easily do damage, and the damage can be permanent. So we don't want to lose our hearing at age 22 or whatever, and then live the rest of your life needing hearing aids and whatnot. So anyway, but I asked a question down here sort of in the middle: why would anyone listen to their iPod at full volume? Well, there are a couple of reasons. Maybe you want the music to be louder, it sounds better, whatever. But really the answer is that because you can, because there is a full volume setting there. And now in terms of an iPod, Apple has some safety limits in place. An iPod at full volume is about 115, and so if you listen to it at full volume, for even 45 minutes, you're looking at possible permanent hearing damage. Small changes in decibels equate to usually pretty large changes in perceptual sound levels, and also energy levels go up quite a bit. As you can see at the very bottom here, a 20 decibel increase in a sound is a 10 times physical pressure intensity increase, but it only corresponds to a 4 times over loudness increase. So you see, as you increase the decibels by 20, going up in this scale, you're increasing the physical intensity greatly, and of course that can do damage to your hearing. You see, a vacuum cleaner falls somewhere between city bus and subway train, roughly 90 decibels. Some common levels right there. Many really loud rock concerts are, on the order of, they can hit peaks of 130 decibels, and so they can be dangerous to your hearing. Okay, I don't mean to sound like an old fogey, but be careful. All right, now we're going to talk about the ear, the anatomy of the ear. This is something, it's good to know the parts, just like we covered the eye. The ear is also made up. It's a fascinating apparatus. It really is the coolest thing. And check out this graphic. It's nice. You see the waves coming in, that thing wiggling in there. I put that up because it's cool, and I know you guys like that kind of stuff. All right, 3 main parts. The pinna, okay? The outer, this is the weird looking, fleshy thing on the outside, made of cartilage. That's what we usually call our ear, but that's only the beginning. Okay, so the outer part of the ear, anatomically, would include the pinna, this the cartilage part on the outside of your head. The auditory canal, which you can see channels the sound in towards the eardrum or tympanic membrane. The middle ear is made up of the smallest bones in the human body, the ossicles, the hammer, anvil, and stirrup. There are 3, kind of forming a triangular arrangement, and that transfers the sound into the inner ear, which involves that snail-looking thing that's curled up there, and indeed cochlea is French for snail. The cochlea in the vestibular system, which maintains balance. See those little arches on the top of the snail, of the cochlea. And those are the semicircular canals. We won't get into that too much. We're just going to stick with hearing today. All right. Just a nice graphic to orient you. So you can check that out, refer back to it if you want. Of course, I'll be posting this. I have posted this, obviously, if you're listening to it, and I'll also post just the PowerPoint presentation. You can look at that, flip around, whatever you want to do. All right, starting from the outside here, the anatomy of the ear, the pinna. Really, it's probably the weirdest looking thing on the human body. I mean, if you ask me. Very strange. Why is it shaped like that? Well, for a couple of reasons, actually. It breaks down the sound waves in such a way as to prevent some of weird resonance occurring in the ear. And you can test this, and I've done this before, of course, being involved in crazy experiments. You can actually put clay or silly putty, is what I did as part of an experiment. Put silly putty, you're going to fill up the area of your ear, but you put it around a pencil so that you still have, and you pull the pencil out, you've got a hole that transfers the sound into your ear. But the shape of your ear is nullified essentially by this silly putty that's filling up. And so you listen to the world that way, and it sounds like you're kind of listening to the world through a seashell, that echoey, weird sound. It's very uncomfortable, and I'm glad my ears are weird shaped if they can help make the world sound a lot better. Okay. The auditory canal, it's a channel, basically a tunnel, leads to the eardrum, also known as the tympanic membrane. And this little tympanic membrane, it's a drum. You'll note that the name tympanic from timpani, okay, a timpani drum in a symphony orchestra. It's a tight drum, and so, like any drum, it's sensitive. It'll resonate, vibrate with sound, and so you channel sound down to the tympanic membrane, and it vibrates. And get this, the tympanic membrane is so sensitive that it can signal, it moves to sound pressure that moves it. We're sensitive to sound. That moves the tympanic membrane less than the width of a hydrogen atom. So think about that. I mean, that's incredible sensitivity. I mentioned with vision, we're sensitive to lights that potentially are only made up of one single light packet, one quantum, one photon of light. Same thing here. We're so sensitive to sound that we can pick up on something that wiggles the eardrum just less than the width of a hydrogen atom. I mean, that's infinitesimally small. Okay. The hammer, the names that I don't care if you remember these names, hammer, anvil, stirrup, or malleus, incus, stapes, the same thing. Hammer, anvil, stirrup, if that's easier for you, that's totally fine. That's what you'll see on the test. This is the first bone in the chain of the ossicles. Okay, then it articulates with the anvil, also known as the incus. Slightly larger bone, you can see in the graph here where the incus is. Okay, and they're named for their shape. The hammer kind of looks like a hammer, again the anvil, and then the stirrup, the actual smallest bone in the body. It looks like a little stirrup that you would step into to get onto a horse, if you're familiar with that. All right. All of these things move in and out when they move in and out with the movement of the tympanic membrane. Okay, and they kind of connect to the cochlea. Okay, and this little opening called the oval window, and that sends signals into the fluid of the inner ear. And the cochlea, speaking of the inner ear, this is the spiral-shaped structure, looks like a snail again. And this is where the sound gets transferred into electrical signals that the brain recognizes. This is where the receptors are, these fine little hair cells. They send signals down. You see the auditory nerve to the brain. All right, and that's the part of the brain that sound goes to is the temporal lobe. Okay, and that's where we process all sorts of auditory information, including speech. There's a membrane inside the cochlea called the basilar membrane, and it's wound up in that spiral, and it signals pitch, the pitch of a sound, low versus high. Okay, so you can, in the very beginning, it happens to be high-pitched information, And then if the sound is lower frequency, then it diffuses back further along in that spiral, and it tickles the receptors that are sensitive to lower frequencies, and then those signals, of course, tickle the right hair cells, and it sends information to our brains about the pitch. It's all quite fascinating. When you think about the ear, it's mechanical, it's biochemical, it's neural. It really combines everything that a human sensory system can do. Check this out. Okay, here are the ossicles next to a dime. Okay, they are indeed the smallest bones in the human body. You see that little stirrup there on the right. Teeny tiny. All right, extremely important. Okay, you take one of those bones out of the chain and you don't hear much. Okay, so pretty cool. Now, we've got this air-fluid interface that we have to overcome. Now, I mentioned that sound going through fluid is much more efficient. Right? It travels 4 times as fast. The sound is maintained better. Okay. The problem is we need to get sound out of the air and then transfer it to the fluid of the inner ear inside the cochlea. The problem with transferring sound energy from air to fluid is that a ton of the energy is normally lost. And this is tricky because we want to maintain what's out there and transfer it to our inner ear so it can get to the brain and we can respond appropriately to sounds. So the ear needs to compensate for the loss. It's sort of like if you're underwater and your mom comes out, you're in a pool or something, and she says, "Lunchtime," and she yells, you don't really hear. You might hear something that's muffled, maybe, because she's yelling from the air, trying to reach your ears under the water, all right, in the pool. The ear ingeniously overcomes this. Okay, it has to compensate again for this loss of pressure. How it does it? First of all, it acts as kind of a lever system here, and it's pictured here in this little graphic. You see the eardrum, this large round surface. The ratio of the eardrum to the little footprint of the hammer is very large, and so you're actually creating kind of this lever pressure system. All right, and you can see this little post. It's not normally there. You get this triangular setup, and it acts as a lever. And then this lever system, it coupled with this pressure differential of the eardrum diameter, amplifies it by 1.3. What you get is a compensation of about 29 decibels. It's been calculated to be 29 or 30 decibels. Okay, and so amazingly, the loss from air to fluid is about 29 or 30 decibels. So the ear perfectly compensates for this loss. It amplifies the signal getting into the cochlea so we don't lose anything. It's actually sort of amazing that works that way. Now, if you damage something, you say, for instance, you have a punctured eardrum. It's a common injury, actually, and the eardrum will heal on its own. And some of you may have had, a perforated eardrum, okay, a torn eardrum for whatever reason. It'll sound a little bit like you're underwater, okay, and things will sound muffled, okay. They don't sound crisp, and they'll sound, generally speaking, lower intensity because you're losing this amplification, and also you're losing the transfer from air to fluid. It becomes more of just a loose, sort of a fluid sound. So it'll sound a little like you're underwater. Typically, that's what people report. And then, you get this perfect compensation. Here's a nice electron microphotograph of this arrangement of the ossicles. Pretty neat. And so this is in part how we get that compensation. All right, the inner ear. Now, this is where the action takes place for the ear, analogous to the retina in the eye. We talked about the photoreceptors existing there in the retina. This is where the receptors are for hearing, inside this cochlea. And you see the sound coming from the left there in the middle, hitting the eardrum, hammer, anvil, stirrup, and then we've got this arrangement now that the cochlea has been uncoiled here, so you can see it laid out, and then that membrane on the bottom, the basilar membrane, contains the hair cells that vibrate, again, according to the frequency that's coming in. Those hairs that are closest to the stirrup, this first, or I should say the last of the ossicles in the chain, they're most sensitive to higher frequencies. All right, and then as you go along, it becomes, middle, and then towards the end, low frequencies. And then any extra pressure is diffused out of this thing called the round window at the very bottom. So if you get a lot of energy, it doesn't just get bottled up in your ears and then they pop like that. The popping in your ears caused by pressure differences, altitude differences, is channeled through the eustachian tubes below, and that's where the popping comes from. Part of it is the pressure differential inside the inner ear gets diffused out of that bottom part where that final arrow is appearing to go out of the ear, and then you get that popping. Thankfully, that's in place. If you've ever flown in an airplane with a cold or a sinus infection or something like that, oh my God, God help you. It's brutal because you can't actually, relieve that pressure, and it can be debilitating and very painful. Okay, here is the basilar membrane sort of wound up like you would see it in the cochlea. You see this part at the bottom where the red arrow was pointing to, that's right as the sound is coming into the ear. And those hair cells on the basilar membrane are sensitive to very high frequencies. You see 20,000 here. Progressively, it gets lower and lower as you go around the spiral, okay, to the very low frequencies that are processed in the very inner part of the inner ear. Now, it's thought that this high frequency loss that I mentioned earlier is partly due to the fact that all sound energy, regardless of frequency, has to travel past this part of the membrane. It always is exposed to sound, and so those hair cells just, for lack of a better term, get worn down over time. Also, higher frequency means higher energy, and so what that means is that the hair cells that are sensitive to high frequencies simply have to deal with higher energy sounds, that the frequency is very high. Same thing with vision. You remember, the shorter the wavelength, technically the higher the frequency of those violet lights, maybe 400 nanometers. Same thing, it can do potentially more damage to your eye, to the retina. Okay, so there it is laid out for you, frequency coding in the basilar membrane. This is just kind of funny. It's a while ago now, 8 years or so. Adult-proof ringtone. You guys have heard about this, no doubt. Some teens are reportedly using a ringtone so high-pitched that most adults cannot hear it. Some funny comments here. Anyway, but the funny thing is that these work. I mean, you can have a ringtone that is too high for your parents to hear, all right, because you can still detect it. And so just because you can't hear it doesn't mean it's not there, right? Of course, you can also put your phone on vibrate. Okay. Loud sound. You guys may or may not have heard of this. This is back in 1883. An island off of the coast of Jakarta in the Indian Ocean exploded. This is a volcanic island. Very, very loud. Again, talking about decibel scales. And remember, about 135 to 140 decibels is instantaneous damage to your auditory system. So consider that in some of these figures. The sound of the explosion produced pressure waves of 180 decibels. So anybody that was anywhere near this, again, within a few miles of it, was rendered deaf instantly. Okay, the sound could be heard as far as 3,000 miles away. That's pretty impressive. That's like Los Angeles to New York City. You could actually hear a sound. It was that loud. Okay, pretty wild. You'll see at the bottom there I've got a link to some information. I think it's the wiki page. You can check it out if you're interested. It produced tidal waves that were 120 feet high. So if you're a surfer, that might be kind of exciting, but I'd be scared to death, frankly. Okay. Nearly 2/3 of this island, it was completely blown apart. Estimated that the explosion lifted the island a mile high. So obviously this was sort of a, like almost a biblical event that occurred. Out of control. Check this out. Chunks of coral from the explosion were hurled 20 miles onto surrounding land masses. These chunks weighed 600 tons. You can see the gentleman standing there next to it. Pretty wild. Okay, the volcanic ash in the atmosphere, it lowered the global mean temperature of the Earth by 1.2 degrees Fahrenheit. That lasted for about 5 years. So anything that does that obviously is a massive event. You probably are familiar with this painting, Edvard Munch, The Scream. Anyway, it's thought that this painting was inspired. It was painted around the same time as the Krakatoa explosion, and Edvard Munch was, oh gosh, I want to say Dutch, may have been German, I apologize, but he was thought to be inspired by this, by the beautiful sunsets, because of the ash in the sky. The same thing today. If you live in an area, a big city, maybe with a lot of pollution, air pollution, you'll see beautiful sunsets. Same kind of effect there. All right, maps to better orient you. Haha, orient, pun intended. Orient just meaning east. New York City is the B. All right, and then A is where this thing occurred. Nobody heard this in America. That's way, it's farther than 3,000 miles away. Moving in a little closer, you see the Jakarta Bay. A is on Jakarta. The Krakatoa was out in that bay and threw the chunks of coral onto Jakarta, the coast. So, pretty wild. All right. I like to bring in some stuff like that occasionally just because it's cool. All right, here we go. All right. Built-in protection. You might say, oh my gosh, what do? We have, these loud sounds that sometimes we listen to, sometimes we don't even want to listen to them, but they happen. Maybe it's a firecracker or something like that. Do we have any protection against these sounds? Well, as it turns out, we do. It's a really, really cool mechanism that can protect us, especially from sustained loud sounds. It's called the acoustic reflex. So you've got a high intensity sound stimulus. It takes a little bit of time to develop. It vibrates the tympanic membrane greatly. This stapedius muscle, stapedius and tensor tympani muscles, they work to stiffen the ossicular bones. Okay, they stiffen them and they reduce, this poor tympanic membrane that's vibrating very, sort of intensely. It stiffens that so it doesn't have to vibrate as much, and that doesn't transfer as much energy to your inner ear where it could do damage, right? So the stapedius stiffens this ossicular chain. It pulls the stapes. The tensor tympani muscle stiffens the ossicles by tightening the eardrum, pulling the malleus. So you've got a couple of little muscles in there that work. Pretty awesome. They reduce the incoming pressure to the middle ear. So you get this protection. It reduces pressure by quite a bit, 20 decibels. Again, that's 10 times intensity decrease if you reduce it by 20 decibels. Very interesting. When you chew, swallow, cough, sneeze, and speak, there we go, these muscles work. And so you can do this if you put a piece of gum in your mouth and listen to some music or something like that that's kind of roughly a constant volume, and chew. You'll notice that every time you clamp down your teeth to chew on the gum, the volume will slightly go down. It's pretty cool. It's probably best to do a vacuum cleaner and try this. You're running the vacuum cleaner. It's a fairly constant noise that's occurring. And then if you chew, also if you cough, that'll trigger the acoustic reflex. Sneezing as well. If you cough and sneeze and the acoustic reflex is not in place, you can actually damage your ears. Believe it or not. Okay, when you speak, the acoustic reflex also kicks in. So, otherwise, I would really get sick of hearing myself talk because it'd be too loud. All right. Lastly, here, I apologize for the jumbled up nature of that, but unfortunately, there's this about 20 thousandths of a second, pretty fast, but 20 millisecond delay in the reaction to the loud stimulus. So, like a firecracker or a gunshot or something like that can do damage to your hearing because there's not enough time for the acoustic reflex to build up, to tighten that ossicular chain. Okay, I hope that makes sense. So, of course, you've got to be ready in those cases. Maybe earplugs, something like that. Some kind of ear protection would be recommended, of course. Music at a rock concert, your ears actually do serve to, reduce the sound because it's loud. And the acoustic reflex is like, whoa, settle down, we're going to tighten this up. So you do have some protection. There are very loud sounds that nevertheless will happen during, for instance, a rock concert, and they can hurt you. So even just stuffing some cotton balls or something like that in your ears is recommended. At least it's some kind of All right. So, ears. I ask people, okay, we have, 2 eyes. Why? Well, you can see more, the visual field. You can also, it aids in depth perception. How about ears? Well, you can localize sounds. You can hear left and right, of course. Our ears are placed laterally on our heads. We can localize, though, as well. Your brain makes these really precise calculations to let us know that a sound is either coming left, right, front, back, above us, what have you. All right. How does it do this? Well, the time it takes, of course, sound has a speed, and so a sound coming from the left is going to reach your left ear first by a slight bit faster than your right ear. And the ears in the brain work together to compare the relative time of the sound arriving. It says if it hits the ear left on the left first, it's coming from the left, and you look over to the left towards the sound. Okay. If you've got a cold, and your head, you got a head cold and it's kind of stuffed up, these abilities are greatly compromised. All right. You might have experienced that and wondered why I can't tell where sound's coming from. Somebody will call me from one room and I can't tell where they're calling me from. It's it can be compromised by a head cold for sure. And that's just because sometimes one ear is affected more than the other. So you get differences in especially the intensity here. I got listed second. The intensity, again, the sound, if it hits the ear first, generally speaking, it's going to be processed as more intense. And so that is calculated by the brain as being, okay, it's coming from that direction where it's most intense. Okay. Now, we don't localize low-frequency sounds very well. You can hear them, for instance, like a jet flying above. You hear the low frequencies of the jet. And if you've ever done that and looked up in the sky and thought, I can't really tell where that's coming from, you have to look for the jet, the plane flying over, right? Same thing with like a surround sound home theater system. You've got this thing, the subwoofer, that puts off the low frequency sounds. You can put that subwoofer anywhere in the room. Okay, it can be behind you, it can be up in the corner of the room somewhere. It doesn't matter where that thing goes because we don't really localize the low frequency content of the sound very well. The vocal range, the vocals and the higher frequency, relatively middle and high, those speakers need to be in the right place so that we can hear the sound coming from where it's supposed to be coming from. All right, now, what else contributes to localization of sounds? The pinnae. This is the plural of the pinna, the fleshy, cartilaginous part, the ear. All right, they're important for front and back judgments, so where a sound is coming from, either the front or the back. I mentioned earlier the silly putty experiment that I did. Well, part of that experiment, really the purpose of it, was to determine, the ability to localize sounds when you take the pinnae out of the equation. You fill it in with the silly putty. You leave a little hole in the middle again, so sound can get through. And I was still pretty good at left and right judgments, actually really good, kind of normal performance. But front and back, could not tell. Had no idea. Now normally, of course, the ear is kind of canted where it's catching the sound coming from the front, and it's blocked a little bit from the back. You lose that when you fill in the pinnae, and it effectively renders them useless in terms of localization. So it's pretty interesting. So I was, it's just chance. I would just have to guess. No idea if it was coming from the front or the back. Echolocation. We do this. We actually use this. You make sounds you take for granted because you have vision and you can navigate the environment that way. But if you've ever been in a a very dark room or whatever, and you can kind of tell where the wall is before you run into it because of the sound that's being released or produced by your feet walking along the ground or whatever. It's subtle, but you can tell. Bats and dolphins, of course, as I've referred to earlier today, use this ability to hunt, probably language in terms of dolphins. They chatter all the time. I can't do that sound, by the way. That's pretty awesome, people who can do that. The crazy dolphin sound. But anyway, this sound goes out and it bounces off of objects and they navigate and they talk to each other, whatever. Have you ever, seen a person who is blind? And what do they usually bring around with them? Possibly a guide dog, you might say, but if they don't have a guide dog, they've got a stick, a little walking stick. And they what do they do with it? I used to think, well, the stick's just there. They put it out in front of them in case they're going to run into something, and then they know to avoid it, right? Well, really, that's maybe 3 or 4, maybe 5% of the purpose of that stick. Really, if you ever watch them, they drag it along the ground. They tap it on the ground. And I spoke with a gentleman who was blind and used one of these sticks very effectively, and I actually walked around with him in Athens, downtown. Incredible. He was tapping on the ground, and those sound waves went out and bounced off of objects. Maybe it was a parked car, a fire hydrant, plants, whatever happened to be around us on the sidewalk, and he would describe the objects. He knew the frequency content bouncing off of a car, the metal, the plastic, whatever. He knew what that sounded like, and he described it. It's like, about 5 feet over there, I've got a car. Oh, and here's a tree surrounded by a little metal gate in the middle of the sidewalk. So he's describing all of this to me. And it was pretty amazing. So anyway, and we can develop this. Now, he had vision. He was not born blind, but he had lost his vision. I can't remember exactly why, but he had lost it. And he was probably about 50 years old, and he had lost it about 5 or 6 years previous to that. But pretty incredible. You can still develop that ability. And, if you just blindfold yourself and walk around town, I guess, don't do it. But, you could actually hone your echolocations. All right, and this is another cheesy graphic, and that's the only reason I'm showing it, because it's cheesy. The bat is sending signals out. Those signals, by signals I mean high-frequency sound waves. Those waves are bouncing off of that poor, unfortunate moth, who I assume the bat is going to eventually go get. It doesn't. Imagine the bat flying down and eating that moth. I apologize, it doesn't. That would kind of complete the graphic. But anyway, there you go. It works. I saw this special. Gosh, it was probably 15 years ago on television now. And there was I think it was Ripley's Believe It or Not or something like that, some show. And they showed a troop of people in California that they're all blind, and they are a mountain biking club. Incredible. You'd think, that's just kind of crazy. Like, really? Is that even possible? And it totally is possible. What they do is they use principles of echolocation. Same thing we discussed with the walking stick. They have little clickers on their bikes, on the handlebars, and same kind of thing. The host of the show was out riding in a neighborhood with one of these guys who was blind, and he was using his clicker, and it took him to an unfamiliar neighborhood and said, okay, show me what you got, and they rode around together, and the guy rode around just like he could see. No problem. And he was describing objects off to the side of the road. It's like, okay, up 30 feet ahead, we've got a parked car. I've got to avoid that. Describing trees, bushes, whatever. Acutely using hearing to localize. And then I remember this funny part. He just started taking off, the guy who was blind. Took off in front of the host of the show, who was also on a bike. He takes off, and he's going, 20 or 30 miles an hour towards a parked car, and the host goes, no, stop, and the guy finally got up close to the car, and then slams the brakes on, and he goes, I fooled you, so it's like panic moment there. Obviously very good to be able to do that. It's shocking how much we trust our eyes, but you could actually trust and be okay. I love this cat. What did you just say? I mentioned earlier, a while ago now, that we lose high-frequency hearing. And it starts to manifest as a bit of a disability. Usually, I mean, not on everybody, but usually into your 60s or 70s, where the high frequency loss starts to kick into the vocal range. So, you know, you're not able to hear these little high frequency. If you've ever listened to, you know, like me right now talking, the little what they're called vocal plosives, these little ps, ts, ps, you know, you form make a T sound as in talk, or a P sound as in presbycusis, then you can't differentiate D's, P's, T's, those kinds of things, and it throws you way off with speech. And so that's generally speaking when you get a hearing aid or something like that. All right. Again, the death of the auditory hair cells that are, you know, that signal the high frequencies are the ones that go typically first. These are the ones you want to protect. And so how do you protect them? Well, you try not to expose your, you know, auditory system to high sound pressure levels, high decibel levels. And, you know, you take a couple of preventive measures there, and it'll do you a world of good 30, 40, 50 years down the road. All right. This brings us to the portion of our program that you will hopefully appreciate. This is a review. I will also post a little more in terms of, you know, what you should be focusing on. But these are some actual questions that are going to be on the test. I think 8 questions out of these 75. Again, it's multiple choice. The test is going to cover material presented through, I say, today's lecture, the hearing. Okay, so it's going to be, this hearing stuff will be on the test. Everything from the beginning through hearing. All right, focus primarily on the PowerPoint files for this test. All right, primarily. Okay, and these will all be posted on ELC. Your notes from class will help as well. There are occasionally things that I will say that, you know, add to the material. All right, scanning, reading the book will serve to enhance your chances of doing well. Please read the text with emphasis on the material that I presented in class. It's a lot of material, I understand, and this is why I'm giving you kind of a guide to what's going to be on there, and then I'll also show you in a second here what the test questions will look like. All right, be sure to bring a number 2 pencil. I'm going to bring the Scantrons. Well, maybe not me. A couple of my assistants. There should be about 3 people in there administering the test. Now, the following questions here are actual questions on the test. Here's the first one. A psychic claims that he can read the minds of people on the planet Zipton, which is millions of light years away. The main scientific objection to this claim is that what? I'm not going to give you the answer here, but hopefully you kind of know it and will figure it out. Don't email me about it. Talk to your friends. Look it up. It's not that tough. These will all be easily answered by looking at the PowerPoint slides, which you would normally do to study anyway. All right, next one. Which of the following is an operational definition of intelligence? There we go. What's an operational definition? It's where you put a number to something. What is intelligence? Well, you can say it's when somebody's smart. Well, we're not looking for that. We want to put a number to it, right? Okay, there's a big hint. Next one. An experimenter announces, this is an experiment on hypnosis. Although the experimenter does not actually hypnotize anyone, most of the participants behave the way they believe hypnotized people do. These results are an apparent example of the effects of something, right? Okay, again, I really wish I could give you the answers, but I'm not. I'm going to be... Okay, next one. Getting into the neuron. Remember we talked about this. The numerous short, widely branching fibers of a neuron that receive input from other neurons are known as... That's an easy one. Okay. Again, I'll also have these posted on the PowerPoint, so don't feel like, you know, you've got to listen to me talk about this stuff again in this version of the file. Parkinson's disease is thought to be caused by a deficiency in the activity of the neurotransmitter. What? You guys all know that. I know you do. All right. Conversion of energy from the environment into a pattern of responses by the nervous system is called blank. Making sense of it is called what? All right. about what percentage of humans are born with a blind spot in their retinas? Nobody. I ain't got no blind spot. You might. You know the answer, right? Suppose someone has damage to the hair cells just at the stirrup end of the basilar membrane. That's from today's lecture. That person will have most difficulty hearing which frequency of sounds. Okay. Hopefully that's an easy one for you. Just went over that. Okay, that is it, guys. In terms of questions, feel free to email me. Okay, if you have questions. Try to work through something if you've got a question first. Obviously, there are 300 of you. I want to help all of you. I may also set up a discussion board on ELC so that we can all work together in this, and there may be a time where we can just go crazy, answering questions. Hopefully, if you have a question, then everybody will possibly have that question as well, and I can answer many questions at once. Try to make it efficient. Okay, well, hopefully you got a lot out of this, and I apologize I'm not actually able to be in class. Unfortunately, it happens sometimes. But, hopefully this helps you guys, and I will see you on probably next week. So, anyway, have a good one, and remember, I'll keep you posted on ELC about everything that's happening. All right, see ya.